I would like to thank, of course, Isabella for the kind introduction, for the, let's say, possibility to have this eco-to-fuel workshop within this important conference. Also, would like to thank Vito, because also Vito is involved in this serious conference. So it is of course an honor for us presenting the results of eco-to-fuel in this conference. And I also see that there is so many people connected online, but you have missed a very nice place. Very, you know, the weather today is not so nice like yesterday, but yeah, it is a really a nice place. So yeah, it is also a nice conference. So my presentation is mainly focused on the CO₂ reduction mechanism. Of course, a lot of let's say conjectures from our side, but I thank Faria for the overview of the project, and of course I will just focus on some aspects. Probably Faria has presented the most updated results. I will focus on some initial results, but with the main, let's say, attention on the mechanism. So, as already mentioned by Faria, the production of sustainable fuel is an effective strategy to mitigate, you know, all issues related to the climate changes and of course the increase of the global temperature, and because it is a carbon neutral process, so we don't have net emissions of carbon dioxide into the atmosphere. Of course, this is important in the, let's say, transition period towards complete decarbonization, but for some applications we'll still need some, let's say, hydrocarbon fuels, like in the aviation. It is difficult to implement hydrogen there, so it is really important having some sustainable fuel. And of course, there are several approaches to reduce CO₂ electrochemically, and we have focused our attention on low temperature AM water CO₂ co-electrolysis. We have essentially focused on copper-based electrocatalysts. This is, you know, the state of the art in this field, because there is a moderate, let's say, mild binding energy of carbon monoxide, you know, to copper. Carbon monoxide is an intermediate for CO₂ reduction. And understanding CO₂ reduction reaction at copper nanoxide, copper oxide nanoparticles is extremely important, because we want to drive the process towards specific products. Faria already mentioned, our aim is to get carbonaceous fuels with high molecular weight, possible liquid fuels, but unfortunately at the moment it is not the case. We get mainly ethylene in our process, but I will try to let's say, discuss why ethylene is, of course, a preferred route compared to ethanol or other fuels. Coming back to the zero gap cell that was shown by Faria, some initial results were obtained using a small single cell, and this is just the let's say the scheme of the single cell operation. It was already discussed by Faria. I will want to mention that the CuOx solution is just fed to the anode. So some CuOx solution is permeating through the anion exchange membrane to the cathode. Of course, we want to avoid cathode flooding, because CO₂ must reach catalytic sites. So if we have a flooded cathode, of course, there is no reaction with CO2. CO2 cannot cannot reach catalytic sites. This is very important. And for this specific AM electrolysis technology, we operate the system at 50 degrees Celsius. And and we measure the products at the outlet. Our analytical setup is based on let's say 3 types of gas chromatographs, because the outlet from the cell is passed through a cold trap. In this cold trap, we just, let's say, separate liquid products from gas products. And as an example, ethanol is entrapped in the cold trap in the liquid phase, and ethylene is ethylene, hydrogen, carbon monoxide, of course, are forming the gas phase. And we have a TCD, a gas chromatograph, using a TCD detector for, let's say, small molecular weight gases like hydrogen, carbon monoxide, CO2. And we have the flame ionization detector for ethylene, methane, etc. And for the liquid products, we make sampling at the end of the test. So we collect all liquid at the end of the test, and we make sampling, and we analyze by gas chromatograph coupled to mass spectrometer. We always use nitrogen as an internal standard, because all the integration of these peaks is done with reference to the nitrogen internal standard in order to avoid, let's say, discrepancies. So regarding the materials, I would like to just say a few words on the cathode and the anode materials, but my colleagues will discuss this more in detail in the following presentations. We use copper oxide nanoparticles, 20 nanometers crystallized sites. This is a tenorite structure. Copper monoxide. In principle, we start from cuprite, but after thermal treatment of the electrode, we get copper monoxide. Of course, during the electrochemical reaction at the negative potential, you can have also change of the oxidation state, change internal restructuring of the material, but our starting point for the electrode is copper monoxide tenorite. And for the anode, nickel iron LDH, well known in this field, with small crystallized size in the range of 8 nanometer. Both electrodes are quite porous. Now, what is really important is to focus on the polarization curves, because this is the first test that usually is carried out. And as you can see, of course, these are not regarding the best electrodes that were shown by Faria, but some initial electrodes. We, at the beginning, have investigated the effect of ionomer dispersion or electrodes cathodes without ionomer. The situation is that in the presence of ionomer dispersion in the cathode layer, you can see much better performance, but in the case of the electrode, the cathode without ionomer, of course, larger activation region and, of course, lower voltage efficiency. But, the best performance with electrodes containing ionomer dispersion is essentially due to the evolution of hydrogen. Our goal in this case is to avoid or reduce the competition from hydrogen. So we have observed that we need hydrophobic electrodes, so we have to remove the ionomer because, of course, we want to avoid the flooding of the cathode by water. We need a good balance between CO2, assessing the catalytic sites, and water, but of course we need to avoid excess of water. This is an important aspect that we have observed in our work, and now I just can show, Faria has shown, let's say, a long-term test. Here I'm just focusing on a short-term test, 24 hours. The voltage is quite stable to the end. At the end, we have a rise in cell voltage again, and this is just for us an indication that some clogging of the cathode occurs, and we need the flushing of the cathode. Unfortunately, the environment is alkaline, and you may understand that the CO2, of course, is precipitating if there is no sufficient amount of water. And since we need to balance the hydrophobicity and the water content of the cathode, some precipitation will occur under these conditions. The analysis was carried out during the day, not during the night. It is manual start of the analysis for the gas analysis. You can see there is a prevailing production of hydrogen, but also suitable amount of ethylene, 40% of ethylene in this case, something like 5% of carbon monoxide at 300 milliampere square centimeter and 2.5 volts. It is important to mention the current density is extremely important because this is linked to the capital costs of the electrolyzer. We want to operate at high current density because we decrease the capital costs of the electrolyzer. But we also need to work at a high voltage efficiency. 2.5 volts is, let's say, suitable voltage efficiency. You can see in the literature there are, of course, better results in terms of Faraday efficiency, but Faraday efficiency is not sufficient to assess the performance of an electrolyzer. Energy efficiency, voltage efficiency is extremely important because at the moment we are using a high cost renewable electricity. The final cost of renewable fuel, the final cost of hydrogen in conventional electrolyzers at the moment is mainly affected by the cost of renewable efficiency and the uptime hours. So after having discussed these aspects, you can see at the end of the test, 50% hydrogen, 40% ethylene, 5% carbon monoxide, about 5% ethanol and propanol. And now the question is why we get ethylene instead of carbon monoxide? Why ethanol is so low concentration? So it is important to understand what happens in terms of mechanism at these, let's say, copper oxide electrodes. So Faria has already shown the reversible potential for the three main reactions: reduction of CO2 to carbon monoxide, reduction of CO2 to ethylene, and to ethanol. Of course, if we need to form ethylene and ethanol, we need 2 molecules of carbon dioxide per molecule of ethylene and ethanol, 1 molecule in the case of carbon monoxide. And the number of electrons involved in the carbon monoxide formation is 2 electrons. In the other case, we have 12 electrons. So you, of course, may think that the process of forming ethylene is more complicated than carbon monoxide, but indeed the situation is opposite because we produce much more ethylene. And in terms of thermodynamics, you know, the ethylene is slightly more favored compared to carbon monoxide, 200 millivolts about difference. Ethanol is comparable to ethylene, but still ethylene is preferred towards ethanol in terms of reaction yield. So now let's try to, how to say, to understand why ethylene is the preferred route, and we can discuss a little bit the reaction mechanism that we have recently published in Chemical Engineering Journal. So for more details about the reaction mechanism, you can have a look to this publication. And you know, the first step is the absorption of carbon monoxide that can form linearly bonded carbon monoxide. This is, you know, an important step because Of course, you need a catalyst with suitable chemisorption energy for carbon monoxide. And you know that, as an example, in fuel cells, carbon monoxide, in the past, hydrogen fed in fuel cells anodes was from reforming of natural gas, hydrogen, so containing some traces of carbon monoxide. And of course, carbon monoxide was poisoning for platinum because there is, let's say, a strong interaction. The interaction is electron donation through sigma bonds from carbon monoxide to the metal, to the transition metal, and you have a back donation of electrons from the orbitals of the transition metal to the empty 2π orbitals, 2π stars, molecular orbitals of carbon monoxide. These, let's say, donation and back donation is the, let's say, the main aspect that, of course, influences the strength of carbon chemisorption on the surface. However, copper, this binding energy to copper is much less strong than in the case of platinum, but also less strong than in the case of nickel and iron. So copper is a suitable catalyst because of this labile bond formation, and you can have release the, let's say, desorption of carbon monoxide in this case, and of course you will see carbon monoxide in the products. But if you have a suitable coverage of carbon monoxide absorbed on copper catalyst, you can have this carbon-carbon coupling. So you have this let's say, bridge bond. In this case, this bond is the initiate the formation of ethylene and ethanol. And this subsequent mechanism is a nucleophilic attack of the adsorbed molecule of the adsorbed intermediate to water. You may understand that the catalyst is surrounded by water molecules. So, of course, under cathodic conditions, you have such excess of electrons on the surface, and of course, these electrons can be transferred. So with this nucleophilic attack, so you get hydrogen and release hydroxide ions that migrate through the membrane to the anode. And this step is a sequential step of water attack and the rearrangement of the molecule, and some, of course, some detachment at the end, because otherwise you cannot get ethylene. But this means stronger bonding between the adsorbed intermediate and copper catalytic sites, and at the end you have the formation of this intermediate. This intermediate has been detected with infrared spectroscopy and Raman, and was and this is well known in the literature. There is a, let's say, we'll say, some agreement on this intermediate, where you have a carbon-carbon coupling, but still this intermediate can evolve to ethylene or can evolve to ethanol. If you consider the evolution to ethylene, this must pass through the attachment of hydroxide group, stronger formation, and subsequent, let's say, nucleophilic attack to water, and hydrogen uptake, electron uptake, release of hydroxide, and at the very end you have a detachment from the of the bond between the adsorbed molecule and the catalytic side, and you get, of course, ethylene at the end. This process is simple. There are no relevant reaction steps that can, let's say, slow down the reaction rate. But if you move to, if you consider the mechanism for ethanol, the mechanism for ethanol formation is much more complicated, because in this case, in the case of ethylene, the first step is, of course, the detachment of, let's say, OH group. In the case of ethanol, this means that one bond between the adsorbed intermediate and the catalytic site should give rise to a nucleophilic attack to water. And in this case, you have, of course, this intermediate that is not, let's say, like in the case of ethylene, let's say bond to two catalytic sites, so the intermediate is very stable on the surface. In this case, is a complicated situation and without good stability, but there is also the need for an isomerization step, rearrangement on the surface, formation of a stronger bond with catalytic site, and thereafter nucleophilic attack and evolution of ethanol. So according to the reaction mechanism, it is clear why ethylene is the preferred route compared to ethanol. It is matter of internal let's say, desorption of, let's say, detachment from one bond to the catalytic site. It is matter of internal rearrangement. And of course, there is an associated higher activation energy compared to ethylene. So at the moment, we need to balance. So there is also another aspect that I would like to emphasize. In the case of ethanol, we need more water. There is an additional need of water molecule, but if we have a look to the mechanism, the role, the initial attack by water is very important. So if we, let's say, feed more water, if we have more flooded electrode, we can get more ethanol. But the situation is, if we provide more water to the cathode, of course, we have more flooding. So we also favor hydrogen evolution. So we need a delicate balance between water at the cathode and the CO2 access to the catalytic sites. And under this configuration, ethylene seems to be the preferred route. So we have an excess of ethylene. With this, I would like to conclude. We have observed that using a zero gap cell, using a copper oxide electrocatalyst, we can get a good voltage efficiency in the range of 65%. It is not yet approaching the voltage efficiency of hydrogen electrolyzers. You know, most advanced hydrogen electrolyzers can get 80% voltage efficiency, but we are not so far. Of course, much lower current density. This is an important aspect, but the aim is to produce, of course, carbonaceous fuels, not just hydrogen. At the moment, with the best electrodes that have been shown by Faria now, we can get 60% Faraday efficiency to ethylene. For this specific study, the ethylene was about 40%, but the total organic products were 50%, so comparable to hydrogen evolution. In my opinion, of course, if we can get a better understanding of the reaction mechanism, we can design a more advanced electrocatalyst for this process if our aim is to produce liquid fuels. And of course, we need to depress hydrogen evolution because it is a competitive reaction. So with this, I would like to conclude. I thank you very much for your kind attention. I would like to thank the CO2 project and the financial support from the European Commission, our coordinator, Faria, and Isabella for the kind opportunity to provide our results within this interesting conference. Thank you. If are there any questions from the audience and from online, please.
Very nice part. I just want to ask what kind of membrane?
Yeah, the membrane used in this work is provided by Hydrolyte. Hydrolyte is a company from Israel that is working on, let's say, an exchange membrane. Unfortunately, they do not disclose the chemistry. I have some idea what chemistry is behind. I have to say that also there was some agreement with De Nora. They are now also in, let's say, in agreement with De Nora for providing this membrane. So unfortunately, cannot say much. Probably Alessandra can say something. I don't know, not more, but I can say 100, approaching between 50 and 100 millisiemens per centimeter hydroxide conductivity. Regarding the hydrogen content in the oxygen stream, that is an important aspect. I have not mentioned this, but this is important for safety issues. This is lower than 2% under our conditions. So it is a good material. The thickness used in this study is something like 70 microns. Alessandra, can you go? For 50, I was remembering 70 at the okay, between 50 and 70, yeah, let's say. And yeah, I have to say also good selectivity for hydroxide. Alessandra has made some measurements comparing selectivity for hydroxide, for chlorides, for bromides. There is a very good selectivity for hydroxide. And yeah, it is, they have produced in rolls of several meters, because for the 1 megawatt plant that they have produced, let's say, 100 meters of rolls of this membrane. So it is the hydrolyte. It is let's say, suitable for scaling up. I cannot say much more, unfortunately. Yeah, the binder. Yeah, the ionomer binder was from a hydrolyte as well. This ionomer dispersion, it is a shredded membrane that is dissolved in suitable solvents. We can get under ultrasonic, let's say, stirring. We can get a good ionomer dispersion. This ionomer dispersion is combined to the anode catalyst and spray coated on PTL, on nickel PTL, nickel mesh, from back to form the anode. Regarding the cathode catalyst, we have tested the configuration with ionomer and without ionomer. The configuration with ionomer is electrochemical, much more performing, but you have a prevailing hydrogen evolution because there is absorption of solution from the electron. The hydrophobic configuration without ionomer is instead much more suitable for CO₂ reduction, but of course with lower voltage efficiency in the overall polarization curve. I think I have disclosed so many aspects. So. Okay, I see some okay, I see some okay. I don't know which. I cannot see the presentation. Okay, is there any degradation and how did you estimate it? Okay, I think how did you get it? Okay, I don't know which was the first question.
I think it's this one.
Yeah. Thank you for sharing this work. May I ask how the washing procedure was carried out? Just water. So this is let's say, warm water that is flushed through the cathode with the cell under rest potential. So the current is stopped during this process. The second question is, thank you, okay, manufacturer, why you choose catalyst coating membrane, CCM and not CCS? No, probably I was not sufficiently clear. We indeed use CCS, not CCM. So we coat, De Nora coats the catalyst onto the gas diffusion electrode for the cathode and onto the nickel felt for the anode. So it's a catalyst coated substrate. It is not a CCM for the moment. How did you get all materials out of the cell? Not materials, but products. Yeah, for the products, of course, there is a flushing of CO₂ through the cathode. So this CO₂ flow is transporting products at the outlet. Cold trap can separate liquid products from gaseous products. And we measure, of course, after partialization, we measure the gas chromatograph. So
In situ.
In situ, yeah, in situ. Is there any degradation? Yes, of course, there is some degradation. The first degradation is the clogging issues. The environment is alkaline, CO2 give rise to some precipitation. In order to mitigate this, we humidify CO2 at a temperature higher than the cell temperature. But we need to flush the cathode after some time. If you don't need to flush the cathode, for sure you have a flooding of the cathode with the poor carbon dioxide conversion. Yeah, just will be sure. Oh, thank you very much. Okay, if you are feeding a 1 molar KOH at the anode and you commonly have a CO2 crossover to the anode via M, how do you manage neutralization? Of course, the membrane is much more selective towards hydroxide ions compared to carbonate ions, but we also, of course, flush anode, and we change regularly the KOH. KOH recirculating through the cell is regularly changed, so in order to avoid also some issues at the anode. The other question is, okay, in general, MEA is suitable for making liquid products, and do crossing through the GDA and out of the cell via CO2 chamber. In this case, we use let's say our architecture is zero gap cell, so instead of alcohols, we have a minimal amount of alcohols, we have more ethylene. Yeah. I'm sorry. There are so many answers. I don't know if these are collected from our colleagues at Meta, and I will try to answer offline eventually. If you can, provide your email address to our colleagues of Meta, I will provide my answer offline. We need to move to the next presentation. So thank you once more for your kind attention.